Welcome everyone, and thank you for being here today as we embark on a fascinating journey into the world of logic. In a world awash with information and diverse viewpoints, the ability to think clearly and reason effectively has never been more critical. Logic is the foundation upon which we structure our thoughts, analyze arguments, and arrive at sound conclusions. It is an essential skill that transcends disciplines and influences every facet of our lives. As we navigate through the complexities of contemporary society, we are constantly bombarded with claims and counterclaims, persuasive rhetoric, and emotional appeals. In such an environment, how can we discern truth from falsehood, valid reasoning from flawed reasoning? This is where the study of logic comes into play. Logic equips us with the necessary tools to dissect arguments, assess their validity, and understand the underlying principles that govern sound reasoning. In today's lecture, we will explore several fundamental principles of logic, starting with the nature of deductive and inductive reasoning. Deductive reasoning allows us to arrive at specific conclusions based on general premises, where the truth of the premises guarantees the truth of the conclusion. On the other hand, inductive reasoning deals with drawing general conclusions from specific instances, acknowledging that while such conclusions may be probable, they can never be guaranteed. Understanding the distinction between these forms of reasoning is crucial as they each serve unique purposes in our thought processes. We will also discuss the structure of arguments, focusing on components such as premises and conclusions, and the ways in which these components interact to form coherent arguments. By breaking down arguments into their constituent parts, we can more easily identify strengths and weaknesses, helping us to evaluate their overall effectiveness. Moreover, as we delve deeper into our discussion, we will shine a light on common logical fallacies, errors in reasoning that can lead us astray. These fallacies, which often appear persuasive at first glance, can undermine rational discourse and cloud our judgment. Familiarizing ourselves with these pitfalls prepares us to recognize them not only in the arguments of others but also in our reasoning, fostering clearer thought. Finally, I will encourage you to contemplate the practical applications of logic in your everyday lives. Whether in academic settings, workplace scenarios, or personal relationships, the principles of logic can guide you toward more thoughtful interactions and better decision-making. The ability to articulate clear, rational arguments can enhance your persuasive abilities and deepen your understanding of complex issues. As we proceed, I invite you to think critically and engage with the material presented. Logic is not merely an academic subject. It is a vital skill that can empower you to navigate the world with clarity, confidence, and creativity. Together, let us unlock the mysteries of reasoning, strengthen our analytical abilities, and appreciate the beauty of logical thought. Now let us dive into the first topic of our exploration: the distinction between deductive and inductive reasoning. To begin, let's further elucidate our definition of logic. Logic is not merely an abstract notion confined to textbooks, rather it is a comprehensive framework that synthesizes the principles of valid reasoning and argumentation. It is an intellectual discipline that seeks to clarify how we think, how we formulate arguments, and how we ascertain the validity of those arguments. By systematically studying these principles, logic enables us to refine our thinking processes and enhances our ability to communicate effectively. Now let's explore the core focus of logic: how conclusions follow from premises through correct reasoning patterns. Imagine engaging in a discussion about climate change. You might begin with premises such as human activities release greenhouse gases, and these gases lead to global warming. From these premises, one might draw the conclusion that human activities contribute to climate change. This process illustrates deductive reasoning. If the premises hold true, the conclusion is inescapable. Logic enables us to articulate the relationship between premises and conclusions clearly and rigorously, allowing us to construct arguments that are not only persuasive, but also grounded in sound principles. Furthermore, logic encompasses a variety of reasoning patterns, including both inductive and deductive reasoning, each serving distinct roles. Deductive reasoning, as we've discussed, seeks to provide conclusions that are necessarily true if the premises are true. In contrast, inductive reasoning draws generalized conclusions from specific instances, often utilizing patterns and observations to infer broader principles. For example, if you observe that the sun has risen in the east every day of your life, you might conclude that the sun always rises in the east. While this conclusion may be reasonable, it is not absolutely certain, as it is based on repeated observations rather than definitive proof. Logic provides tools for assessing the strength of such inductive arguments based on the quality and quantity of observations. We also must consider the informal reasoning that takes place in everyday discussions. Here, we often simplify complex arguments, relying on heuristic devices that may lack rigorous structure, but remain deeply ingrained in how we communicate. For example, in a casual debate about a political issue, one might appeal to popular opinion or anecdotal evidence. While such methods can be persuasive, they can also lead us to commit logical fallacies, errors in reasoning that detract from the validity of our arguments. Understanding these fallacies is integral to our exploration of logic, as it empowers us to recognize when reasoning goes awry, whether in our own arguments or those presented by others. The foundational nature of logic is evident in its applicability across disciplines. In the realm of mathematics, for instance, logical principles underpin proofs and equations, ensuring that conclusions are founded on rigorously established truths. In science, the scientific method itself is steeped in logical reasoning, guiding researchers to formulate hypotheses, conduct experiments, and draw conclusions based on empirical data. Even in fields like law and ethics, logic is crucial for constructing coherent arguments, interpreting statutes, and determining moral principles. Moreover, logic fosters critical thinking, a skill indispensable in our rapidly evolving world. As technology advances and information becomes increasingly accessible, the ability to sift through vast quantities of data and varying perspectives is paramount. Logic empowers individuals to engage in higher-order thinking, allowing for discernment between credible evidence and misleading assertions. It encourages us to question assumptions, analyze arguments critically, and approach complex issues with a reasoned mindset. As we further our exploration of logic, we will unlock various techniques and methodologies that enhance our reasoning abilities. From examining formal systems to exploring natural language arguments, the principles we uncover will not only contribute to our academic growth, but also equip us with skills applicable in everyday life, from problem solving to effective communication. In summary, logic is a profound and essential discipline that encompasses the study of reasoning, argumentation, and critical thought. It serves as the bedrock for rational discourse in all domains, enabling us to articulate our ideas clearly, assess the validity of others' arguments, and engage thoughtfully with the world around us. I invite you to reflect on the significance of logic in your own lives as we delve into specific aspects of reasoning and argumentation in the upcoming sections of our lecture. To fully appreciate the discipline of logic as we know it today, we must journey through its rich historical evolution, tracing its roots from ancient origins through the medieval period and into the modern era. Each phase of this evolution has contributed to the development of logical principles, expanding our understanding and application of reasoning across various fields. We begin our exploration in ancient times, where the foundation of logic was laid by arguably its most significant figure, Aristotle, who lived from 384 to 322 BCE. Aristotle is often hailed as the father of formal logic, having developed the first comprehensive system of logical reasoning known as syllogistic reasoning. His work, notably encapsulated in texts such as Prior Analytics, introduced a method of argumentation that involved deducing conclusions from two premises. For example, in a classic syllogism, one might argue all humans are mortal, premise 1, Socrates is a human, premise 2, therefore Socrates is mortal, conclusion. Aristotle's systematic approach not only categorized different types of syllogisms, but also established rules for determining their validity. This pioneering work has influenced subsequent generations, embedding logic as a fundamental tool for philosophy, science, and rational argumentation. As we transition into the medieval period, we witness the expansion of logical thought, particularly within the frameworks of religious scholarship. Scholars such as Avicenna, an influential Persian philosopher, and Thomas Aquinas, a medieval Christian theologian, played pivotal roles in integrating Aristotelian logic with theological inquiry. Avicenna built upon Aristotle's concepts, introducing new logical forms and refining syllogistic reasoning to align with Islamic philosophy and metaphysics. Similarly, Aquinas sought to harmonize Aristotle's teachings with Christian doctrine, emphasizing the importance of logic in theological discourse. His works, particularly the Summa Theologica, illustrate how logic could elucidate religious truths, thereby enriching both philosophical and theological discussions. This synthesis of logic and faith during this period led to the establishment of logic as a critical component of education in medieval universities throughout Europe. The landscape of logic underwent a profound transformation during the modern era, spurred by the intellectual revolutions of the 19th and early 20th centuries. Figures like George Boole, Gottlob Frege, and Bertrand Russell introduced mathematical approaches to logic that redefined how reasoning was understood. George Boole, in his groundbreaking work The Laws of Thought, developed Boolean algebra, a system that uses algebraic methods to express logical propositions and relationships, paving the way for symbolic logic. This marked a significant shift from traditional syllogistic forms to a mathematical representation of logical expressions, which later became foundational in the fields of computer science and digital logic. Following Boole, Gottlob Frege significantly advanced the landscape of logic with his formalization of predicate logic, a system that allows for more complex relationships beyond those expressed in traditional syllogisms. Frege's insights laid the groundwork for modern mathematical logic, emphasizing the importance of quantifiers and variables in logical formulations. Finally, Bertrand Russell, along with his collaborator Alfred North Whitehead, sought to resolve paradoxes that emerged in set theory through their monumental work, Principia Mathematica. Their efforts not only contributed to the rigor of logical foundations, but also sparked philosophical discussions about the nature of truth, meaning, and language, further intertwining logic with philosophy and mathematics. The wave of innovation initiated in this era resonated well into the 20th century, influencing philosophers, mathematicians, and computer scientists alike. As we reflect on the history of logic, we see a continuous thread from Aristotle to the modern era, where each thinker and school of thought has pushed the boundaries of rational discourse. Logic has evolved from a system of syllogisms to a sophisticated framework that integrates mathematical precision, philosophical inquiry, and practical application. This historical journey not only enhances our understanding of logic, but also emphasizes its relevance in our contemporary world, where the ability to think critically and clearly remains paramount. In contemplating the question, why study logic, we uncover a multitude of compelling reasons that highlight the significance and applicability of logical reasoning in our lives. Logic is a versatile tool that enhances various cognitive skills and enriches our understanding across disciplines. First and foremost, studying logic profoundly enhances our critical thinking abilities. In an age where we are inundated with information from various sources, be it the internet, social media, or traditional news outlets, having the skills to analyze and evaluate complex problems becomes imperative. Logic sharpens our capacity to discern fact from opinion, identify biases, and evaluate the validity of arguments. By learning how to break down propositions into their core components, we can assess their strengths and weaknesses with greater clarity. This analytical rigor allows us to approach problems systematically, leading to more thoughtful and informed conclusions. Whether we are evaluating a political argument, analyzing a research study, or simply choosing between options in daily life, applying logical reasoning empowers us to navigate complexities with confidence. Moreover, the applications of logic extend far beyond the realm of philosophy. It proves to be invaluable across a range of disciplines. In mathematics, logic forms the backbone of proof construction and theorem validation, providing a framework for understanding relationships between concepts. In computer science, programmers use logical principles to create algorithms and troubleshoot software, translating logical reasoning into practical applications that drive technological advancements. Similarly, in law, logical reasoning is essential for constructing legal arguments, analyzing cases, and interpreting statutes, allowing lawyers to present their cases in a compelling manner. In scientific research, logic aids in hypothesis formulation, experimental design, and the interpretation of data, grounding conclusions in rational inquiry. This cross-disciplinary applicability underscores the universal nature of logical principles and highlights their importance in producing meaningful contributions across various fields. Furthermore, one of the most practical benefits of studying logic is its ability to facilitate better decision-making. In both professional and personal contexts, logical reasoning encourages us to weigh the evidence, consider alternative perspectives, and evaluate potential consequences before reaching a conclusion. When faced with complex decisions, be it hiring an employee, selecting a product, or confronting ethical dilemmas, applying logical principles helps us navigate uncertainty and arrive at rational choices. This disciplined approach fosters a sense of responsibility in our decision-making processes, as it encourages us to base our actions on reasoned judgment rather than on impulse or emotional response. Additionally, the study of logic fosters effective communication. By understanding the structure of arguments and the lexicon of reasoning, we become better equipped to articulate our thoughts clearly and persuasively. A well-constructed argument can influence opinions, drive discussions, and promote constructive dialogue. In both collaborative settings and public discourse, the ability to present ideas logically and coherently enhances our credibility and fosters respectful, informed exchanges. Lastly, engaging with logic cultivates intellectual curiosity and a lifelong love of learning. The pursuit of knowledge through logical inquiry encourages us to question assumptions, challenge conventions, and explore new ideas. It instills an appreciation for the intricacies of reasoning and the value of rigorous thought, nurturing a mindset that embraces inquiry, skepticism, and open-mindedness. In summary, the study of logic is not merely an academic exercise. It is a vital endeavor that enriches our cognitive skills, enhances our analytical capabilities, and broadens our understanding of the world. Through enhanced critical thinking, cross-disciplinary applications, improved decision-making, and effective communication, the principles of logic empower us to engage with life thoughtfully and responsibly. As we continue our exploration of logic, we will delve into specific logical concepts and techniques that will further sharpen our reasoning skills and enhance our capacity for thoughtful discourse. As we explore the fundamental concepts in logic, we find that they serve as the cornerstone for constructing valid arguments and engaging in sound reasoning. Understanding these concepts allows us to communicate clearly and persuasively, as well as to evaluate the arguments of others. Let's begin with conclusions. A conclusion is the statement that follows logically from the premises in an argument. It is the assertion that the argument seeks to establish as true based on the evidence provided. Conclusions are crucial because they encapsulate the primary claim that we intend to convince our audience to accept. For example, consider the argument, if all humans are mortal, and Socrates is a human, then it follows that Socrates is mortal. Here, the conclusion is, Socrates is mortal. The conclusion represents the logical endpoint of the reasoning process, and its strength depends entirely on the truthfulness and relevance of the premises that lead to it. A well-formed conclusion not only reflects sound reasoning, but also provides a clear message that can influence thought and action. Next, we look at arguments. An argument is a structured set of statements or propositions, including premises and a conclusion, designed to establish the truth of that conclusion based on the premises. The efficacy of an argument is assessed through its validity and soundness. Validity refers to the logical structure of the argument, whether, if the premises are true, the conclusion must also be true. Soundness, however, takes this a step further. An argument is sound if it is not only valid, but also has true premises. For instance, consider this argument. 1. Premise 1. If it rains, the streets will be wet. 2. Premise 2. It is raining. 3. Conclusion. Therefore, the streets will be wet. This argument is valid because the conclusion logically follows from the premises. If both premises are true, the conclusion must also be true, demonstrating sound reasoning. Arguments can be classified into deductive and inductive categories. Deductive arguments aim to provide definitive conclusions, while inductive arguments derive generalizations based on specific observations, leading to probable conclusions. Each type of argument has its applications across various fields such as science, law, and everyday decision-making. Now let's delve into premises, the foundational elements of any argument. Premises are statements accepted as true within the context of the argument and act as the supporting evidence that leads us to the conclusion. They are critical because they provide the groundwork for the conclusions drawn. Strong premises are typically based on empirical evidence, sound reasoning, or widely accepted facts. Here's a simple example for further clarity. 1. Premise. All birds have feathers. 2. Premise. A sparrow is a bird. 3. Conclusion. Therefore, a sparrow has feathers. In this example, the premises convey universally accepted information about birds, which allows us to confidently arrive at the conclusion. To ensure an argument holds weight, it is vital that the premises are not only true, but also relevant to the topic at hand. If we were to introduce a premise that lacked relevance or truth, the overall argument could be weakened or invalidated. Lastly, we turn our attention to statements. A statement is a declarative sentence that expresses a proposition that can be classified as either true or false. In logic, statements form the essential language through which arguments are articulated. Understanding statements is crucial for analyzing arguments, as they are the components that comprise premises and conclusions. For instance, the sentence, "The sky is blue," is a statement that can be evaluated for its truth depending on the context. Statements are distinct from questions, commands, or exclamations, as they assert information that can be measured for accuracy. The relationship between these four concepts is integral to logical reasoning. Conclusions depend on premises, which are comprised of statements. An argument is formed by associating premises with a conclusion. By comprehensively understanding these concepts, we empower ourselves to construct coherent arguments, engage critically with the arguments of others, and participate in rational discourse. In consideration of practical applications, the study of these basic concepts equips us with skills that extend into everyday decision-making. Whether we are evaluating news articles, engaging in debates, or conducting scientific research, the ability to differentiate between premises and conclusions, recognize the structure of arguments, and analyze statements for truthfulness helps us navigate the complexities of information we encounter. As we continue our study of logic, we will delve into specific types of arguments, logical fallacies that can arise, and methods for evaluating the strength of arguments. This deeper exploration will further sharpen our reasoning abilities and enhance our capacity for thoughtful engagement in various contexts. In the realm of logic, statements are fundamental as they represent declarative assertions that can be evaluated for truthfulness. Statements can be classified into three main types: simple statements, compound statements, and quantified statements, each serving a distinct function in logical discourse. Let's begin with simple statements. A simple statement is a basic declarative assertion that conveys a single idea and cannot be broken down into smaller components. These statements are the most straightforward form of expression in logic, providing foundational building blocks for more complex reasoning. For instance, the statement, "Socrates is a man," is a simple statement. It's a clear declaration that can be classified as true or false. Similarly, the statement, "The sky is blue," is also a simple statement. Each of these examples encapsulates a singular proposition that does not require additional context or elaboration for understanding. Simple statements are critical in logical reasoning because they form the basis for more complex arguments and allow us to construct and analyze premises and conclusions effectively. Next, we move on to compound statements, which arise when two or more simple statements are combined using logical connectives. Logical connectives are words or phrases used to link statements in a way that expresses a relationship between them. The most common logical connectives include and, or, and not. A compound statement asserts a relationship between its constituent simple statements. For example, consider the compound statement, "Socrates is a man and all men are mortal." This statement combines two simple statements through the connective and, asserting that both claims are true. Alternatively, we might encounter the compound statement, "The sky is blue" or "It is raining," which uses the connective or to indicate that at least one of the two conditions holds true. Compound statements are invaluable in logical reasoning as they allow us to create more nuanced assertions, enabling the construction of arguments that reflect complex relationships between various claims. Furthermore, we encounter quantified statements, which express propositions about all or some members of a particular group. These statements utilize quantifiers such as all, some, or none, to make broader assertions that apply to sets of objects or individuals. For instance, the statement, "All humans are mortal," is a quantified statement that asserts a universal truth about the entire group of humans. It indicates that mortality applies to every member without exception. On the other hand, a statement like, "Some birds cannot fly," makes a particular claim about a subset of the group of birds. Here, the quantifier some allows for variability within the group, indicating that not all birds possess the ability to fly, but at least a few do not. The importance of quantified statements in logic lies in their ability to convey generalizations and relationships across larger sets. They allow us to express truths that encompass extensive categories, which is particularly useful in mathematical reasoning, scientific theories, and philosophical discussions. For example, in mathematics, quantified statements like, "For every x, if x is an even number, then x is divisible by 2, provide clear definitions applicable to entire classes of numbers. Each of these types of statements plays a crucial role in the structure of logical reasoning and argumentation. Simple statements convey individual assertions. Compound statements establish connections or relationships between those assertions, and quantified statements generalize findings to broader categories. Together, they enrich our ability to construct logical arguments, analyze propositions, and engage in meaningful discourse across various fields. As we progress through this exploration of logic, we will learn how to recognize these different types of statements in arguments, how to evaluate their relationships, and how they contribute to the formulation of sound reasoning. Understanding these distinctions not only sharpens our analytical skills, but also enhances our capacity to communicate ideas clearly and effectively. In logic, the concept of truth values is central to evaluating statements, arguments, and propositions. Truth values determine the validity of the assertions we make and allow us to engage in rigorous reasoning. Let's explore the foundational elements of truth values, what it means for a statement to be true or false, the utility of truth tables, and the role of truth functions. To begin with, we define true statements. A statement is considered true if it accurately corresponds to reality or if its conclusion follows necessarily from its premises. For example, the statement, "Water boils at 100 degrees Celsius at standard atmospheric pressure," is true because it corresponds to established scientific facts. In a logical context, true statements form the foundation for valid arguments. They ensure that the conclusions drawn are reliable and reflective of reality. When evaluating arguments, the presence of true premises increases the likelihood that the conclusion will also be true, depending on the logical structure of the argument. Conversely, false statements are those that do not correspond to reality or that contradict established premises. For instance, the statement, "All humans are immortal," is false because it contradicts the known fact that humans, like all living beings, eventually die. False statements complicate logical reasoning, as they can undermine the validity of the arguments in which they appear. When an argument contains false premises or leads to a false conclusion, its overall effectiveness is diminished, highlighting the importance of verifying the truth values of the statements we use. Now, let's discuss truth tables, which are indispensable tools in logic for illustrating the truth values of compound statements. A truth table systematically organizes all possible truth values for the components of a logical expression, allowing us to examine how the truth values of simpler statements combine to yield the truth value of a more complex statement. For example, consider the compound statement P and Q. In this case, P and Q are simple statements that can each be either true or false. A truth table for this statement would look like the following: P, Q, P, and Q. True, 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 false, 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 true, false, 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 false. In this table, the first two columns represent the possible truth values of P and Q. The third column illustrates the resultant truth value of the compound statement P and Q. As we can see, the compound statement is only true when both P and Q are true. In all other scenarios, it is false. Truth tables can be expanded to encompass more complex statements, reflecting various logical connectives such as or, not, and combinations thereof. Finally, we have truth functions, which refer to operations that determine the truth values of complex statements based on the truth values of their components. Truth functions help us understand how the truth value of a compound statement is derived from the truth values of the individual statements it comprises. For example, in the case of logical connectives, we have 1. Conjunction, and. A compound statement formed by conjunction is true only when both of its components are true. 2. Disjunction, or. A compound statement formed by disjunction is true if at least one of its components is true. 3. Negation, not. A statement created with negation reverses the truth value of its component. If the component is true, the negation is false, and vice versa. Understanding truth functions allows us to analyze logical relationships systematically and predict how changes in the truth values of individual statements will affect the compound statements they form. This analytical framework is crucial not only in theoretical discussions of logic, but also in practical applications in mathematics, computer science, and philosophy. In summary, truth values are fundamental to logical reasoning, forming the basis for evaluating arguments and statements. True statements correspond to reality or logically follow from premises, whereas false statements do not. Truth tables serve as valuable tools for organizing and examining truth values in compound statements, while truth functions provide the operations necessary for understanding how these truth values interact. Together, these concepts enrich our comprehension of logic and empower us to engage in more rigorous reasoning. As we continue our exploration of logic, we will delve into the intricacies of logical connectives, the construction of more complex arguments, and the identification of common logical fallacies, furthering our understanding of sound reasoning. In the study of logic, logical operators are fundamental tools that allow us to construct and analyze complex statements by connecting simple statements in various ways. Understanding how these operators work is essential for evaluating the truth values of combined propositions. The primary logical operators we will examine include conjunction, disjunction, and negation. Let's begin with the conjunction operator, represented by the symbol. The conjunction operator combines two statements, and the resulting compound statement is true only when both individual statements are true. If either statement is false, the compound statement will also be false. The logical structure of a conjunction can be expressed as follows. AB, where A and B are simple statements. For example, if we let A represent the statement "it is raining" and B represent "the ground is wet," the conjunction AB means it is raining and the ground is wet. To evaluate the truth value of this compound statement, both A and B must be true. If either is false, if, for example, it is not raining but the ground is wet due to a different cause, the whole conjunction is false. Next, we have the disjunction operator, denoted by the symbol. Disjunction combines multiple statements and asserts that the compound statement is true if at least one of the individual statements is true. It provides a more flexible relationship between the components. The logical structure is expressed as AB. For instance, if A is "it is snowing" and B is "it is raining," the disjunction AB means "it is snowing" or "it is raining." In this case, the compound statement is true if either it is indeed snowing, raining, or both. The only scenario that renders the entire disjunction false is if both A and B are false. Lastly, we examine the negation operator, represented by the symbol. Negation is unique because it does not combine two statements but rather reverses the truth value of a single statement. When we apply negation to a statement A, the result is A, which means not A. For example, if statement A represents "the sky is blue," then A would mean "the sky is not blue." Negation alters the truth value directly. If A is true, the sky is indeed blue, then A is false. And if A is false, the sky is not blue, then A is true. This considerable operation is crucial in logical reasoning because it allows us to express opposition and alternative scenarios. To summarize the logical operators we've discussed: 1. Conjunction, and. Symbolized by, this operator produces a true compound statement only when both connected statements are true. Example, AB. 2. Disjunction, OR. Denoted by two keys, this operator yields a true result if at least one of the statements is true. Example, AB. 3. Negation, not. Represented by, this operator reverses the truth value of a single statement. Example, A. Understanding how to formulate statements using these logical operators allows us to create complex logical expressions and analyze their truth values effectively. As we work with these operators in future discussions, we will explore more intricate logical expressions and consider how various combinations can be used to build sound arguments or identify logical fallacies. As we move forward in our exploration of logic, I encourage you to think critically about how these operators function in everyday reasoning and discourse, as recognizing them will strengthen your analytical capabilities in evaluating statements and arguments. Conditional statements are a fundamental concept in logic, crucial for reasoning about cause and effect relationships and implications. The basic structure of a conditional statement can be expressed as if P, then Q, which is symbolically represented as P. Q. In this framework, P is referred to as the antecedent, the condition, and Q is the consequent, the result. For example, consider the statement, if it rains, P, then the ground will be wet, Q. Here P and Q are clearly defined, establishing a direct link between the condition and its outcome. To analyze conditional statements further, we need to consider the concepts of necessary and sufficient conditions. 1. Necessary condition. A necessary condition for P to be true is that Q must also be true. This signifies that if P occurs, then Q must also occur. In other words, P cannot be true without Q being true. Using our earlier example, for the statement, if it rains, then the ground will be wet. Having a wet ground, Q is a necessary condition for the rain, P. If it's not raining, then the ground might not be wet. confirming that the wetness of the ground is dependent on the occurrence of rain. 2. Sufficient condition. Conversely, a sufficient condition refers to a scenario in which P guarantees the truth of Q. This indicates that if P is true, then Q must also be true. In our example, if we assert, if it rains, then the ground will be wet, we view rain as sufficient for the ground's wetness. However, the ground could also be wet for other reasons. For instance, it could be watered by a hose, indicating that while rain ensures a wet ground, it is not the only possible cause. Importantly, sufficient conditions do not imply exclusivity. Instead, they are simply a guarantee for the consequent when the antecedent is satisfied. Next, we explore related forms of conditional statements, each of which modifies the original statement in a way that can produce different logical implications. These forms are known as the contrapositive, converse, and inverse. 1. Contrapositive. This form takes the original conditional statement, if P, then Q, P, Q, and flips and negates both the antecedent and the consequent, resulting in, if not Q, then not P, Q, T, P. The contrapositive is logically equivalent to the original conditional statement, meaning that if P, Q is true, then Q, P is also true. For example, from our earlier statement, if it rains, P, then the ground will be wet, Q, the contrapositive would be, if the ground is not wet, Q, then it did not rain, P. 2. Converse. The converse of a conditional statement flips the antecedent and consequent, resulting in if Q, then P, Q, P. This transformation does not maintain logical equivalence. The truth of the converse does not necessarily follow from the truth of the original statement. For example, the converse of if it rains, P, then the ground is wet, Q, would be if the ground is wet, Q, then it is raining, P, which may be false if other factors, such as a water sprinkler, contribute to the wet ground. 3. Inverse. The inverse negates both the antecedent and the consequent of the original conditional statement, resulting in if not P, then not Q, when Q. Like the converse, the inverse does not retain the truth of the original statement. For instance, the inverse of if it rains, P, then the ground is wet, Q, would be if it does not rain, P, then the ground is not wet, Q, which is also potentially false for similar reasons. Understanding these variations in conditional statements, particularly how they relate to necessary and sufficient conditions and their various forms, is critical for logical reasoning. It enables us to determine relationships between different propositions and assess the validity of arguments we encounter. In real-world reasoning, the ability to recognize conditionals and their related forms is important in fields such as mathematics, philosophy, law, and scientific inquiry, where conditional reasoning often forms the basis of conclusions drawn from empirical evidence or theoretical frameworks. As we continue our journey in logic, we will explore more complex logical constructions and how to apply these concepts thoughtfully in various contexts. We may also discuss common logical fallacies that can result from misinterpretations of these forms, further enhancing our critical thinking skills. In the study of logic, distinguishing between valid arguments, sound arguments, and invalid arguments is crucial for assessing the effectiveness of reasoning and for engaging in rigorous discourse. Each type of argument has unique characteristics that pertain to its logical form and the truth of its premises and conclusions. Valid arguments. A valid argument is defined by the relationship between its premises and conclusion. An argument is considered valid if, whenever all its premises are true, the conclusion must also be true. Validity concerns itself purely with the logical structure of the argument rather than the actual truth of the premises. In other words, a valid argument ensures that the conclusion follows logically from the given premises, regardless of whether the premises themselves are factually correct. For example, consider the following argument. 1. Premise 1. If it rains, then the ground will be wet. If P, then Q. 2. Premise 2. It is raining. P. 3. Conclusion. Therefore, the ground is wet. Q. This argument is valid because if both premises are true, the conclusion must also be true. However, validity alone does not guarantee that the argument is based on factual premises. A valid argument could have premises that are entirely fictional or false but still maintain a correct logical structure. Sound arguments. A sound argument, on the other hand, takes the concept of validity a step further. A sound argument is one that is not only valid but also possesses true premises. In essence, a sound argument guarantees the truth of its conclusion based on both its logical form and the factual accuracy of its premises. Therefore, all sound arguments will yield true conclusions in reality. For example, let's take a sound argument. 1. Premise. 1. All humans are mortal. True. 2. Premise 2. Socrates is a human. True. 3. Conclusion. Therefore, Socrates is mortal. True. In this case, the argument is valid. The conclusion follows logically from the premises. And because both premises are indeed true, the argument is also sound. This guarantees that the conclusion is true. Socrates is mortal. Invalid arguments. Now, let's turn our attention to invalid arguments. An argument is considered invalid if the conclusion does not necessarily follow from its premises, even if the premises are true. In invalid arguments, it is possible for the premises to be true while the conclusion is false. This failure in logical structure indicates a flaw in reasoning. For example, consider this invalid argument. 1. Premise 1. All cats are animals. True. 2. Premise 2. All dogs are animals. True. 3. Conclusion. Therefore, all cats are dogs. False. In this instance, while both premises are true, the conclusion does not logically follow from them. This demonstrates that the argument is invalid. The structure does not uphold logical reasoning, allowing for a conclusion that can be false even when all premises are accurate. Summary of key concepts. Valid arguments. If all premises are true, the conclusion must be true. Focuses on the logical structure, not the factual truth of premises. Sound arguments, valid arguments that also have true premises, guarantee true conclusions in reality. Invalid arguments. Arguments where the conclusion does not necessarily follow from the premises, true premises can lead to a false conclusion. Understanding the distinctions between valid and sound arguments, as well as recognizing invalid arguments, is vital for effective logical reasoning. It enables us to critique and construct arguments critically, engage in meaningful discussions, and draw reliable conclusions based on logical principles. As we continue our study of logic, we will explore additional concepts such as logical fallacies and how they can undermine sound arguments, further enhancing our analytical skills. Inductive reasoning is a method of reasoning that moves from specific observations to broader generalizations and predictions. Unlike deductive reasoning, which guarantees the truth of its conclusions provided the premises are true, inductive reasoning deals with probabilities and likelihoods. It allows us to form conclusions based on patterns identified in observations, but these conclusions are inherently uncertain. Specific observations. Inductive reasoning begins with specific observations, where we gather multiple instances or examples. This process involves collecting data from real-world experiences, which serve as the foundation for drawing broader conclusions. For example, consider the observation: every observed swan is white. Here, the indeterminate number of swans observed leads to a collection of individual instances suggesting a pattern, even though it may not reflect the entire population of swans. Similarly, another example of specific observations is, the sun has risen every day I have observed. Each instance of the sun rising adds to the pool of evidence that contributes to the reasoning process. Pattern recognition. Next, through pattern recognition, we identify regularities across these observations. By analyzing the specific examples, we look for consistent traits or behaviors that seem to emerge from the observations. In our swan example, if every swan we have encountered has been white, we may start to perceive a pattern suggesting that swans are generally white. In the case of the sun rising, the repeated occurrence establishes a pattern that we may come to interpret as a predictable event. However, it's important to recognize that patterns identified through inductive reasoning do not guarantee certainty. They only point to trends or regularities based on observed data. Probability assessment inductive reasoning also involves probability assessment, where we evaluate the likelihood of the conclusion based on the evidence gathered. This step is critical, as it acknowledges the inherent uncertainties of inductive reasoning. Just because we have observed a trend does not mean that there will be no exceptions. For example, the conclusion that all swans are probably white arises from the observed instances, but no amount of observation can completely rule out the existence of non-white swans elsewhere. Similarly, the conclusion that the sun will rise tomorrow is based on a pattern of repeated observations, yet it remains a probabilistic expectation rather than an absolute certainty. General conclusion. Finally, from the observations and assessed probabilities, we arrive at a general conclusion. This conclusion forms a broader principle or prediction based on the patterns identified earlier. In our example about swans, after observing many white swans, we might conclude, all swans are probably white. For the sun rising, we might assert, the sun will rise tomorrow. While these conclusions are reasonable and drawn from evidence, they carry a degree of uncertainty intrinsic to inductive reasoning. Characteristics of inductive reasoning 1. Probabilistic nature. Inductive reasoning leads to conclusions that are probable rather than certain. We cannot guarantee that the conclusion will be true, even if the premises are based on evidence from observed instances. 2. Flexibility. Inductive arguments can adapt as new evidence or observations emerge. If we observe a non-white swan, our general conclusion about swans must change accordingly. 3. Empirical basis. Inductive reasoning is grounded in empirical evidence from the world. Scientific inquiry often relies on induction to develop hypotheses and theories based on observed phenomena. Importance of inductive reasoning. Inductive reasoning plays a vital role in various fields, particularly in scientific exploration, where scientists formulate hypotheses based on observed patterns and conduct experiments to test their validity. It allows for generalizations to be made, predictions to be formulated, and theories to be developed, guiding further inquiry and exploration. In summary, inductive reasoning moves from specific observations to general conclusions by recognizing patterns and assessing probabilities. While it allows us to make informed predictions, it should always be approached with an awareness of its inherent uncertainties. This understanding helps in both everyday reasoning and the rigorous methodologies employed in scientific and philosophical contexts. As we continue to examine logical reasoning, we may compare and contrast inductive reasoning with deductive reasoning, exploring their respective strengths and limitations. We can also discuss the role of inductive reasoning in understanding and analyzing various real-world situations and phenomena. 1. Ad hominem. The ad hominem fallacy occurs when an argument attacks the character or personal traits of the individual making the argument rather than addressing the argument itself. This tactic shifts the focus away from the validity of the position being presented, and instead targets the person, often to discredit their viewpoint without engaging with the reasoning behind it. Example, Person A, I believe we should implement stricter environmental regulations to combat climate change. Person B, you're just a college student. How can you possibly understand the complexities of environmental policy? In this example, Person B does not address the argument put forth by Person A. Instead, they divert the discussion by questioning Person A's credibility based on their background. 2. Straw man. The straw man fallacy occurs when someone misrepresents or oversimplifies an opponent's argument to make it easier to attack. Rather than engaging with the actual position being argued, the straw man fallacy involves constructing a distorted or weakened version of the argument, allowing the person employing this tactic to refute it more easily. Example, Person A, we should focus on increasing funding for public education. Person B, Person A wants to throw money at schools without any accountability. Here, Person B misrepresents Person A's argument by suggesting that their position is about unconditionally funding schools without oversight. This deviation from the original argument creates an easier target for criticism. 3. False dichotomy, or false dilemma. The false dichotomy fallacy, also known as the false dilemma, presents a situation as though there are only two exclusive options when, in fact, more alternatives exist. This oversimplification forces others into choosing between two extremes, ignoring the nuances and intricacies that could lead to a more balanced discussion. Example, you're either with us or you're against us. This statement creates a false dichotomy by suggesting there are only two possible stances, disregarding the possibility of nuance or middle ground. In reality, there could be various positions a person might hold that do not fit neatly into either category. 4. Circular reasoning. Circular reasoning, or begging the question, occurs when an argument's conclusion is used as a premise to support itself. This reasoning fails to provide any valid evidence or reasoning outside of the conclusion itself, rendering the argument unproductive and uninformative. Example: I believe that reading is beneficial because it is good for you to read. In this case, the statement claims that reading is beneficial by saying it is good for you to read, which is essentially restating the conclusion rather than providing a valid justification or evidence for why reading is beneficial. Importance of recognizing logical fallacies. Recognizing these common logical fallacies is crucial for several reasons. 1. Enhancing critical thinking. By identifying fallacies, we sharpen our analytical skills and learn to engage with arguments more effectively. We can differentiate between valid reasoning and manipulative tactics. 2. Strengthening arguments. Understanding fallacies enables us to construct stronger, more valid arguments by avoiding these pitfalls in our own reasoning. 3. Fostering constructive dialogue. Addressing fallacies helps maintain the integrity of discussions, encouraging participants to focus on the substance of the arguments rather than resorting to attacks or misleading representations. 4. Improving discourse. In both casual conversations and formal debates, learning to point out logical fallacies will elevate the level of discourse, fostering more productive and respectful discussions. In summary, common logical fallacies, ad hominem, straw man, false dichotomy, and circular reasoning represent errors in reasoning that can significantly undermine arguments and discussions. Becoming adept at recognizing these fallacies can improve our reasoning skills, strengthen our arguments, and enhance our critical thinking abilities. As we continue our exploration of logic, we can discuss additional fallacies that commonly arise in arguments, or we can shift our focus to other aspects of logical reasoning or argumentation. Syllogisms. A syllogism is a form of deductive reasoning that consists of two premises followed by a conclusion. It allows for the drawing of logical inferences based on the relationships between categories of statements. Syllogisms are fundamental in classical logic and are essential for analyzing how conclusions can be drawn from general principles. Components of a syllogism. 1. Major premise. This is a general statement that establishes a broad category or principle. It serves as the framework for the argument. Example: all humans are mortal. This statement asserts a universal truth about the category of humans. 2. Minor premise. This is a specific statement that relates to a particular subject or instance within the major premises category. Example: Socrates is human. This statement identifies Socrates as belonging to the category defined in the major premise. 3. Conclusion. This is the logical result that follows from combining the two premises. If both premises are true, the conclusion must also be true due to the structure of deductive reasoning. Example: therefore, Socrates is mortal. The conclusion logically follows from the premises, indicating that because Socrates is a human and all humans are mortal, Socrates must be mortal as well. This structure is often summarized in the form: major premise, all A are B; minor premise, C is A; conclusion, therefore, C is B. Validity of syllogisms. Syllogisms can be evaluated for validity based on their logical structure. For a syllogism to be valid, the conclusion should logically follow from the premises, regardless of whether the premises themselves are factually true. Validity is determined by the logical relationship between the statements. Example of a valid syllogism. 1. Major premise: all mammals are warm-blooded. 2. Minor premise: a dog is a mammal. 3. Conclusion. Therefore, a dog is warm-blooded. In this case, if both premises are true, the conclusion must also be true, demonstrating valid reasoning. Example of an invalid syllogism. 1. Major premise: all cats are animals. 2. Minor premise: a dog is an animal. 3. Conclusion. Therefore, a dog is a cat. Here, while the premises may be true, the conclusion does not logically follow from them, making the syllogism invalid. Venn diagrams. Venn diagrams are a useful visual tool for representing syllogistic relationships between categories. They consist of overlapping circles, where each circle represents a category, and the overlaps illustrate the relationships between those categories. For example, to analyze the syllogism, so 1. Major premise: all humans are mortal. 2. Minor premise: Socrates is human. 3. Conclusion. Therefore, Socrates is mortal. A Venn diagram for this syllogism would have one circle representing humans and another circle representing mortals. Since all humans fall within the circle labeled mortals, and Socrates is part of the humans circle, we can visually confirm that Socrates also falls within the mortals circle. Using Venn diagrams allows individuals to 1. Identify valid forms. By visualizing the relationships, one can easily see if the conclusion logically follows from the premises. 2. Spot invalid forms. Discrepancies or gaps in the Venn diagram can highlight invalid syllogistic reasoning. 3. Simplify complex relationships. They can aid in simplifying and understanding more complex relationships between multiple categories and statements. Importance of syllogisms. Syllogisms are fundamental not only in philosophical debates, but also in everyday reasoning. They offer a structured methodology for drawing conclusions based on logical connections between categories. Mastery of syllogistic reasoning enhances critical thinking skills, enabling individuals to construct coherent arguments and evaluate the reasoning of others. In summary, syllogisms consist of a major premise, a minor premise, and a conclusion, allowing for logical deductions based on categorical relationships. Venn diagrams serve as a valuable visual tool for illustrating these relationships and assessing the validity of syllogistic reasoning. Understanding these structures enhances our ability to engage in effective logic, argumentation, and critical analysis. Propositional logic. A proposition is simply a statement that can be either true or false. We use symbols and notation to represent these propositions and their relationships, which allows us to construct compound statements and evaluate whether they're true or false. Symbols and notation. In propositional logic, we use two main types of symbols. First, we have variables. Propositions are represented by letters like P, Q, and R. Each variable stands for a specific statement that has a truth value, meaning it's either true or false. For example, let's say P represents it is raining, and Q represents the ground is wet. Second, we have logical connectives. These are symbols that connect propositions to form compound propositions. There are four main connectives you need to know. Conjunction, represented by the and symbol, means both statements must be true. So P and Q is only true if both P and Q are true. Disjunction, represented by the or symbol, means at least one statement must be true. So P or Q is true if either P is true or Q is true or both are true. Implication, which we read as if-then, connects two statements. If P, then Q, is false only in one specific case, when P is true but Q is false. In all other cases, the implication is true. Negation, represented by not, simply flips the truth value. Not P is true when P is false, and false when P is true. These symbols allow us to construct complex logical expressions that capture the relationships between various propositions. Truth functions. Each logical connective has a specific truth function that describes how the truth value of the compound statement relates to the truth values of its parts. Let's walk through each one. Conjunction. P and Q is true only when both P and Q are true. If either one is false, or if both are false, then the whole statement is false. Disjunction. P or Q is true if at least one of them is true. It's only false when both P and Q are false. Implication. If P, then Q has a special truth pattern. It's false only when P is true and Q is false. In every other case, when both are true, when P is false and Q is true, or when both are false, the implication is considered true. Negation. Not P is simply the opposite of P. If P is true, then not P is false. If P is false, then not P is true. These truth functions let us evaluate compound statements based on the truth values of their individual parts. Tautologies and contradictions. In propositional logic, there are two special types of statements worth noting. A tautology is a compound statement that is always true, no matter what truth values we assign to its components. For example, P or not P is always true. Either P is true or P is false. One of these must be the case, so the statement is guaranteed to be true. A contradiction is the opposite. It's a compound statement that is always false, regardless of the truth values of its components. For example, P and not P is always false. A statement can't be both true and false at the same time, so this is impossible. Why propositional logic matters. Propositional logic serves as the foundation for more complex logical reasoning. It's used extensively in mathematics, computer science, philosophy, and artificial intelligence. Understanding how to construct and evaluate propositions using logical connectives and truth functions allows us to engage in rigorous analysis, develop algorithms, and construct formal proofs. As we continue studying logic, we can move on to more complex systems, like predicate logic, which extends propositional logic by adding quantifiers and relations. We can also explore practical applications of propositional logic in computing and other fields. Predicate logic. While propositional logic deals with entire statements that are simply true or false, predicate logic allows us to make statements about the properties of individual objects within a domain. This gives us much more expressive power. In predicate logic, we use two key components: predicates and quantifiers. First, we have predicates. These are functions that express a property or relationship among objects. For example, human of X is a predicate that can be true or false depending on whether X is a human. Second, we have quantifiers. These are symbols that specify the quantity of objects we're talking about. There are two primary quantifiers in predicate logic: the universal quantifier and the existential quantifier. Let's look at each one. The universal quantifier. The universal quantifier is represented by an upside-down A symbol, and we read it as for all X. This quantifier indicates that a statement applies to every single member of a given domain. It asserts that for every individual object X in that domain, a certain property holds true. Let me give you an example. Consider the statement: for all X, if X is a human, then X is mortal. This is making a universal claim about every member of the domain. In other words, every human being must be mortal. There are no exceptions. The universal quantifier ensures that this property applies to all humans without exception. The existential quantifier. The existential quantifier is represented by a backward E symbol, and we read it as there exists an X. This quantifier indicates that there is at least one member of the domain for which a certain property holds true. It claims the existence of at least one object that satisfies a particular condition. Here's an example. There exists a bird X such that X does not fly. This statement tells us that at least one member in the domain of birds is unable to fly. This could be a penguin, an ostrich, or some other non-flying bird. We're not claiming that all birds can't fly, just that at least one bird exists with this property. Why predicate logic matters. Predicate logic captures nuances of language and logical representations that propositional logic simply cannot handle. By using predicates and quantifiers, predicate logic gives us two major advantages. First, it provides expressiveness. We can formulate complex statements that describe properties of individuals and the relationships between them in ways that propositional logic can't manage. Second, it offers precision. We get a more precise representation of statements that involve quantification, helping us avoid the ambiguities that often appear in natural language. For instance, while propositional logic struggles to express statements involving words like all, some, or none, predicate logic presents a clear framework to articulate these concepts through quantifiers. This allows for much more effective logical analysis and reasoning. Applications of predicate logic. Predicate logic is essential across multiple fields. In mathematics, many proofs and definitions use predicate logic to formalize statements about sets, functions, and relations. It's the language mathematicians use to be absolutely precise. In computer science, predicate logic is foundational in the development of programming languages, databases, and artificial intelligence. Whenever we need to make statements about objects and their properties in computing, predicate logic is at work. In philosophy, predicate logic helps with philosophical arguments and discussions by providing ways to rigorously express and analyze statements about existence, necessity, and generality. To wrap up, predicate logic expands upon propositional logic by introducing quantifiers and predicates. This enables more nuanced and expressive statements about objects and their properties. The universal quantifier, which we read as for all, makes claims about every member of a domain. The existential quantifier, which we read as there exists, asserts the existence of at least one member with a specific property. By capturing the complexities of language and reasoning, predicate logic serves as a powerful tool in mathematics, computer science, and philosophy. As we continue exploring logic, we can delve into specific applications of predicate logic, or discuss how it relates to other logical systems, such as logical inference, or the important distinction between soundness and completeness. Logical proofs. A logical proof is a formal process that establishes the validity of an argument by demonstrating that the conclusion logically follows from the premises. Logical proofs are essential in mathematics, philosophy, and many fields of science because they provide a systematic way to verify statements and assertions. The purpose of logical proofs. So why do we use logical proofs? They serve three main purposes. First, they demonstrate validity. A proof shows that if the premises are true, then the conclusion must also be true. There's no escaping it. Second, they establish truth. By establishing the truth of the conclusion based on the truth of the premises, proofs provide a foundation for further reasoning and conclusions. Third, they clarify reasoning. Proofs help clarify the reasoning process, allowing others to follow the logical steps that lead to a conclusion. This makes arguments transparent and verifiable. Types of proofs. There are two main types of proofs we'll discuss today: direct proofs and indirect proofs. Direct proofs. A direct proof involves straightforward reasoning from the premises to the conclusion. In this method, the argument is structured in a logical progression, where each step leads naturally to the next in a clear and systematic manner. Here's how a direct proof works. You start with the premises, then you apply logical rules and inference to derive the conclusion. Each step must be valid and supported by either the premises or previously established statements. Let me give you an example. Let's prove the statement. If n is an even number, then n squared is also even. Here's the proof. First, we assume n is even. By definition, this means there exists an integer k such that n equals 2 times k. Now, let's calculate n squared. If n equals 2k, then n squared equals 2k. All squared, which equals 4k squared. We can rewrite this as 2 times 2k squared. Notice that the expression 2 times 2k squared is even, since it's a multiple of 2. Therefore, if n is even, then n squared is also even. In this direct proof, we logically progressed from the premise, which is the definition of an even number, all the way to our conclusion about the result of squaring that number. Indirect proofs. Proof by contradiction. An indirect proof, also known as a proof by contradiction, takes a different approach. Instead of proving something directly, we start by assuming the opposite of what we intend to prove. The objective is to demonstrate that this assumption leads to a contradiction, which then reinforces the truth of the original statement. Here's the structure. First, you assume the negation of the conclusion you want to prove. Then you use reasoning and logic to derive implications from this assumption. Finally, you show that this leads to a contradiction, thereby proving that the original conclusion must be true. Let's work through an example. We'll prove the statement, if n squared is odd, then n is odd. Here's our proof by contradiction. First, we assume the opposite of what we want to prove. So we suppose that n squared is odd, but n is even. Now by definition, if n is even, then there exists an integer k such that n equals 2 times k. Let's compute n squared. If n equals 2k, then n squared equals 2k all squared, which equals 4k squared. Notice that 4k squared is even, since it's a multiple of 2. In fact, it's a multiple of 4. But wait, this means n squared must be even, which contradicts our original assumption that n squared is odd. Therefore, our assumption must be false. This means that if n squared is odd, then n must be odd. Applications of logic. Logic finds extensive applications across various fields, demonstrating its fundamental role in structured reasoning and decision-making. In mathematics and computer science, logic is foundational for mathematical proofs and algorithm design. Mathematical proofs rely on logical reasoning to verify the validity of theorems, utilizing deductive reasoning to derive conclusions from axioms and established results. Additionally, logic underpins set theory, which involves operations on sets and the use of quantifiers to express statements about elements within those sets. In computer science, logical reasoning is crucial for the design and analysis of algorithms, allowing for the determination of their efficiency and correctness. Programming languages also incorporate logical structures and Boolean logic, such as AND, OR, and NOT, to facilitate decision-making in code. Furthermore, logic is significant in formal verification, where techniques like model checking and theorem proving are employed to ensure that software behaves as intended. In the realm of law and argumentation, logical reasoning is indispensable for constructing and analyzing legal arguments. Lawyers rely on logical structures to present cases, interpret laws, and apply legal precedents. Legal reasoning often involves syllogistic logic, where a general law serves as a major premise that is applied to a specific case as the minor premise, leading to a legal conclusion. Furthermore, legal professionals need to critically assess arguments, identify logical fallacies, and argue effectively before judges or juries, making a solid grasp of logic essential for successful advocacy. The scientific method also closely adheres to logical principles, particularly in hypothesis testing and experimental design. Logic guides scientists in formulating hypotheses and structuring experiments, ensuring that the conclusions drawn from research data are valid and reliable. In this context, researchers employ both inductive reasoning, developing general theories from specific observations, and deductive reasoning, testing specific applications of established theories to advance scientific knowledge. Beyond these professional fields, logic plays a crucial role in everyday critical thinking. In daily life, individuals use logical reasoning to evaluate claims encountered in media, advertisements, political discourse, and personal interactions. By understanding and detecting logical fallacies, one can identify weak arguments and misleading assertions, leading to more informed decision-making. Furthermore, applying logical principles allows people to analyze the strength of arguments presented in debates, news articles, or public discussions, fostering better understanding and thoughtful engagement with the information they consume. In conclusion, logic serves as a vital tool across diverse fields, enabling rigorous reasoning and clear communication. Its applications in mathematics, computer science, law, the scientific method, and everyday critical thinking underscore its importance in both professional contexts and daily life. By honing our logical reasoning skills, we enhance our ability to analyze complex situations, construct sound arguments, and engage thoughtfully with the world around us. Tools for logical analysis. Logical analysis employs several effective tools that help formalize and visualize relationships between propositions and arguments, enabling clearer reasoning and understanding. Truth tables are foundational tools used to evaluate compound statements systematically. They provide a structured way to explore all possible combinations of truth values for the individual propositions involved in a compound statement. By laying out these combinations, truth tables allow individuals to determine the overall truth value of the compound statement based on its constituent parts. This method is particularly useful in propositional logic, where complex logical relationships need to be assessed. Venn diagrams serve as visual representations of categorical relationships and set operations. By illustrating sets as overlapping circles, Venn diagrams help to visualize the interactions among different categories or groups. This visualization aids in understanding logical relationships, particularly in syllogistic reasoning and problems involving universal and existential quantifiers. The overlaps indicate shared elements between sets, allowing for a clearer appreciation of logical relationships and operations. Formal proofs establish the validity of arguments through structured sequences of logical inferences. These proofs follow strict logical rules to demonstrate that if the premises of an argument are true, then the conclusion must also be true. Formal proofs are essential in mathematics and logic, as they provide rigorous justification for claims and theorems, ensuring that each step in the reasoning process is logically sound and supported by clear evidence. Logical equivalence is a concept used to identify statements that hold identical truth conditions across all interpretations. Two statements are considered logically equivalent if they produce the same truth value in every possible scenario. Recognizing logical equivalence is crucial for simplifying arguments and understanding the relationships between different propositions, as it allows for substitutions that preserve truth while varying the form of the expression. Beyond these tools, there are additional methods like truth trees and natural deduction that offer specialized techniques for analyzing logical propositions. Truth trees systematically break down complex statements into simpler components, helping to assess their validity by analyzing contradictions. Natural deduction is a method of formal proof that employs a set of rules to derive conclusions based on premises, emphasizing the natural flow of logical reasoning. These analytical tools collectively enhance our ability to formalize and visualize logical relationships. Truth tables evaluate the truth values of compound statements, while Venn diagrams reveal categorical relationships and operations among sets. Testing for logical equivalence helps identify statements with identical truth conditions, facilitating clearer reasoning. By utilizing these various techniques, individuals can engage in more precise logical analysis and refined argumentation, leading to greater clarity and understanding in both academic and everyday contexts. In conclusion, logic stands as an essential discipline that equips individuals with crucial tools for evaluating arguments, enhancing reasoning, and making informed decisions across a multitude of contexts. Through the systematic study of logical principles, individuals can develop skills that are applicable not only in academic pursuits, but also in everyday interactions, professional settings, and decision-making processes. The key takeaways from our exploration of logic emphasize its fundamental role in various domains. First, logic provides a structured framework for analyzing both formal and informal arguments, enabling clearer thinking and more robust conclusions. By learning to apply logical principles, individuals can efficiently navigate complex conversations and discern the validity of various claims. Additionally, logical skills transcend traditional academic boundaries and apply across multiple disciplines. In fields such as mathematics and computer science, logic serves as a foundation for proofs and algorithm design. In law, it aids in constructing coherent cases and interpreting statutes. Furthermore, the scientific method relies on logical principles for hypothesis testing and experimental design, underscoring the universality of logic. Both formal and informal logic enhance reasoning by equipping individuals to engage with a variety of argumentative contexts. Understanding formal logic, emphasizing rigorous proof structures, and informal logic, dealing with everyday reasoning, enriches one's ability to think critically, analyze debates, and construct persuasive arguments. The practical applications of logic are numerous, impacting personal and professional situations alike. One significant application is the ability to detect fallacies in everyday arguments, whether encountered in media reports, political debates, or interpersonal discussions. Recognizing these fallacies enables individuals to engage in more constructive conversations and avoid being swayed by faulty reasoning. Moreover, applying logical principles in the workplace enhances the quality of reasoning and argumentation, proving invaluable for crafting reports, developing software algorithms, or creating persuasive presentations. This logical framework fosters better outcomes and decision-making in professional environments. Similarly, logic supports individuals in making better informed decisions by promoting critical thinking and independent analysis. By employing logical reasoning to evaluate evidence and consider various possibilities, individuals can approach decisions in finance, health, or civic engagement with a more rational mindset. For those eager to continue honing their logical skills, a variety of resources are available to support further learning. Introductory logic textbooks, such as Introduction to Logic by Irving M. Copy or Logic, A Very Short Introduction by Graham Priest, provide foundational insights into the concepts and practices of logic, addressing both classical and contemporary approaches. Online courses in critical thinking offered on platforms like Coursera, EDX, and Khan Academy can guide learners through key concepts in a structured manner, featuring interactive exercises and opportunities for discussion. Additionally, engaging with logic puzzles and brain teasers can serve as both a stimulating challenge and an enjoyable exercise. Collections like the Moscow Puzzles or Logic Puzzles for Dummies offer a fun way to sharpen logical thinking skills. Ultimately, cultivating logical reasoning skills is not merely an academic endeavor. It is an essential practice that enriches personal understanding and fosters productive communication. By embracing logic in thought and discourse, individuals develop a powerful framework for navigating complex information landscapes, thus contributing to informed decision-making and rational citizenship. As you embark on or continue your journey in logic, remember that this discipline has the potential to illuminate paths in your studies, professional endeavors, and daily life.